All right, my talk is about augmentations and Lagrangian fillings. This is a joint work with Dan Rutherford. All right, I'll start the talk by giving a brief introduction of the talk content. Given a Lagrangian knot in the standard contact R3, there are two objects we can consider. The first one is a geometrical object called exact Lagrangian fillings. And these are just surfaces in the symplectization of R3, which is a symplectic R4. And these surfaces are bound by the Lagrangian knot. These are called exact Lagrangian fillings. We consider the embedded ones. And the other one is an algebraic object called augmentation categories. These are invariants that comes from the Chakhanov-Lashberg DGA package. We actually know that embedded exact Lagrangian fillings can induce augmentations. This connection between geometry and algebra is actually very nice and can be extended further. Like in symplectic four manifolds, we can consider Fukaya category, whose objects include exact Lagrangian fillings. And similarly, this side, we can consider augmentation category, whose objects contain augmentations. And furthermore, on the side, Nader and Zaslow shows that Fukaya category objects are actually one-to-one corresponded to macrolocal sheaves on R2. And similarly, in Rutherford, Shendy, Sevak, and Zaslow shows that augmentation category objects are one-to-one correspond to macrolocal sheaves on R2 with the locus on lambda. So you can see that the connection between geometry and algebra are actually extended much more than just object correspondence. Here we can see an inclusion map from the right side to the left side. So it's actually natural to ask whether all the augmentation can be induced from embedded fillings. However, the answer is no. And the natural question here is that can other augmentations come from geometry? So we studied the problem by introducing immersed exact Lagrangian fillings into the picture. And we showed that immersed fillings can also induce augmentations. And furthermore, all the augmentations can be induced in this way. So this is our theorem, which is saying for any Lagrangian and standard R3, all the augmentations can be induced from immersed fillings with their augmentations. All right, now it's the time to take a step back and then talk from the very beginning. I will focus more on the background concepts. So these are pretty standard. Hopefully you have seen these in other one's talk. I will go through these briefly. So first, in this talk, we focusing on R3 with the standard contact structure. These are just like two plane views given by the kernel of a one form. And this one form is just dz minus y dx. All right. And in this contact manifold, we consider Lagrangian knots. These are knots in R3 that are tangent to the contact plane everywhere, which is pretty hard to visualize. To help us visualize that, there are like two ways to do it. First is the front projection, which is projecting to the XZ plane. And the other one is the Lagrangian projection, which is projecting to the XY plane. And these you can see are the front and the Lagrangian projection of N naught and trophil. All right, cool. So Next, we're going to talk about a powerful invariant called Chekhov-Flashback DGA that comes from symplectic field theory. Roughly, well, this DGA is like have very good structure. So basically, we got a functor from the category of Lagrangian to the category of DGA. That is saying for each Lagrangian, there is a DGA associated to that. And furthermore, for each cobordism, which you can view it as maps between Lagrangians, there is actually a DGA map correspond to it, which is very nice structure. Now let's get into more detail. For each Lagrangian, what is a DGA? DGA is a finitely generated Z2 tensor algebra. The generators are actually ribocores of lambda. Here, ribocores are just like vertical line segments with both ends on the Lagrangian. There are finite many of them, so this is like a finitely generated algebra, tensor algebra. And the differential is defined by counting holomorphic disks in the symplectization of Earth ray with the boundary on the cylinder over the Lagrangian. And here we count holomorphic disks with one positive puncture and multiple negative punctures. The differential will map the positive puncture to the product of negative punctures. The DGA, this algebra together with the differential, is a Lagrangian invariant up to a certain type of isotopy. Here you can also view the DGA as a chain complex with an algebra structure. All right, as we mentioned earlier, given the cobordism, there's a DGA map. So first, what do we mean by exact Lagrangian cobordism? That is a surface, again, in the symplectization space, which is R4, and we wanted to have a cylindrical ends over Lagrangian lambda plus and lambda minus. It has compact middle, and there are some other technical conditions for exact Lagrangian, but the takeaway point here is just that the exactness implies that the surface is actually a Lagrangian projection of some Lagrangian surface in a one-dimensional up contact manifold. So given such an exact Lagrangian cobordism, we will get a DGA map from the DGA of the top to the DGA of the bottom. By DGA map here, we just means it's a chain map that preserves the algebra structure. All right, and this DGA map is again defined by counting holomorphic disks in the symplectization space with the boundary on the cobordism. This is again the similar way as we define the differential. All right, the DGA package is like, it's very powerful. It has like a lot of the good algebraic structure, but it's not so easy to compute because the differential is not linear. So the homology is actually hard to compute. But one computable thing from the package is called augmentation. An augmentation of a DGA to Z2 is a DGA map from the DGA of lambda to the DGA Z20. Here Z20 is just the ground DGA, which means the algebra only has coefficient Z2 and no generators, and all the differentials are 0. Another way to think of it is like if you view it as a chain complex, it's Z2 on degree 0 and 0 on other degrees and 0 differentials. So this is an augmentation. Augmentation is just a DGA map. But this algebraic thing can actually have a lot of connection to the geometrical thing, which is the embedded filling we talked earlier, right? So given an embedded exact Lagrangian filling out here, by the functoriality of DGA, we actually get a DGA map from the DGA of lambda to the DGA of empty. And the DGA of empty is actually the DGA with like only with the coefficient, but nothing else. So that's just the ground DGA. And what we get here is exactly an augmentation. So you can see that this augmentation basically just counting how many holomorphic disks bound by each ripcord. You can also view the augmentations as an algebraic extension of the exact Lagrangian fillings. So here what we show is that exact Lagrangian fillings induce augmentations. But as we mentioned earlier, the reverse direction is not true. Not all the augmentations come from embedded exact Lagrangian fillings. The main obstruction actually comes from Seidel's isomorphism. What the saying is that given an exact Lagrangian filling of lambda, it will induce an augmentation. Then the linearized contact homology of lambda with the augmentation epsilon is isomorphic to a singular homology of L with some degree shift. Well, first, this linearized contact homology is just some Floer type homology associated with the augmentation. It's pretty easy to compute because the differential is linearized, so the homology are easy to compute. What this isomorphism tells us is that because we know the right side pretty well, so the left side is kind of like fixed, right? For example, when lambda is a single component knot, then the right side singular homology is fixed, right? And then we know the Poincare polynomial of the LCH is actually t plus 2g. Basically, it's saying the homology of degree 1 is of dimension 1, and degree 0 is of dimension 2 times genus of the surface. There are certainly things like Lagrangian knots whose LCH is in this form, like the trophil, right? The LCH is t plus 2, and it does have a genus 1 surface filling, genus 1 filling. But more knots just don't look like in this way. For example, the mirror 5-2, the LCH polynomial looks in this way, which is far away from the form we would like it to be. Therefore, not all the augmentations come from embedded fillings. So what we did is that we introduced the immersed exact Lagrangian fillings here. By immersed here, we just means everything like before, except we allow immersed point. And remember, the exactness implies that this filling L can be lifted to a Lagrangian in a one-dimensional contact manifold. This Lagrangian is the L tilde, right? So we call this L a good Lagrangian if the L tilde is embedded. So this is a generic condition. We just want it to be good, all right? Given such a good filling, we could do similar things as before, right? We could count holomorphic disk bound by each ripcord, but here we may have some issue because like we may get some negative punctures at the double point, which is joined here, but that's fine. We can just define a map counting all such type of holomorphic disks, and that is a map from the DGA of lambda to the DGA of the filling L tilde. So what we prove is that this map is actually a DGA map. So with this in hand, a further we have some augmentation of the filling L-tilde. We can compose it together and get a DGA map from the DGA of lambda to the DGA of ground, which is an augmentation of lambda. So in summary, what we did is that given a good Lagrangian filling and an augmentation of the filling, we can get an augmentation of the lambda. And what we prove is actually for each Lagrangian in the standard R3, any augmentation epsilon of lambda can be induced by a pair of a good Lagrangian filling and an augmentation of the filling. All right, I guess for the next few minutes, I will go back to the example we had before, which is the mirror of 5-2 here. As we mentioned that, well, first, it has a unique augmentation. And as we mentioned, the LCH is not in the form T plus 2G. It's actually what shows up here. So this Lagrangian does not have an embedded filling. Otherwise, the LCH should look in T plus 2G form. So we will work on this example and show you that this knot does have an immersed filling, and that immersed filling is the one induced the augmentation. Well, to construct an immersed filling, we can do the following thing. So take the part in this box, we can see like two strands, right? Like an I shape here. And then we can pull these two strands away from each other. But remember, when you are pulling the two strands away from each other, you're actually creating a double point because there is a point where your two strands actually meet with each other. So going from here to here, we actually get a double point, and that's called it A. And then once we arrived here, this is just an anode. So you can do Rademaster 1 move to reduce it down and then close it up with a disk. So you just get to empty. And this whole procedure actually built us a filling for this mirror of 5-2. And we know that the filling is just a disk with a single double point A. So our L is a disk filling with one double point. A, and if we count more with more attention, we can see that A actually has degree 2. All right, cool. Well, since this knot has an immersed filling, and the immersed filling can induce an augmentation, and plus this knot has a unique augmentation. So we know that that augmentation actually comes from this immersed filling. Oh, one thing I didn't mention is that here we actually need a pair, right? We need a pair L and an augmentation alpha because this L has one double point. So the algebra of L-tilde is actually an algebra that generated by a single generator A, and the alpha well, it has a unique augmentation, which is sending A to 0. So that is the augmentation here. And with this pair, we can actually induce an augmentation, and plus it has a unique augmentation. So we know that the augmentation actually comes from this immersed fulling. All right. So I guess for immersed filling, we don't have subtle isomorphism anymore, but the LCH still contains certain information. It just like, well, what it is that it's not only considering like containing singular homology of L. It's only like singular homology of L is actually just a part of the LCH. And there are some other parts that are symmetric along degree 0. One side of it will correspond to the LCH of L tilde. So here we have a degree 2 thing, and that will correspond to the T2 part. And the other part will actually be the LCH of L tilde, the dual of that, which means you negative all the generator, the degree of all the generators, and reverse all the differentials, and then you get certain homologies of that. Okay, yeah, so for immersed filling, these LCH of the boundary Lagrangian will not only consider the singular homology of L, it will also contain other informations involve the LCH of the filling as well. All right, I think that's the end of my talk. Thank you for your attention.